Okay, so it's a great pleasure to have with us today Professor Kostas Gourgouliatos from Patras. Kostas started his career from Patras. He was an undergraduate there, but then he moved to Cambridge for his PhD, where he worked with one of the legends of the 20th century astrophysics, Professor Bell. And then he started moving the tortuous path of astrophysicists. I'm telling this for the young people here. So he moved for a first postdoc in across the Atlantic in Purdue University. Then he moved a little bit north after 3 years for another postdoc to Canada in McGill University. Then he crossed again the Atlantic back to Britain, to Leeds for the third postdoc. But then he found a permanent position in Durham, and he became an assistant professor there. But not for long, because Greece was calling him, and so he decided 2 years after he had started his job in Durham to move back full circle to Patras, where he is now an assistant professor. He has won many honorary fellowships and awards. His career is full of these little stars that among them is a Marie Curie fellowship. And his main field of work is basically chemistry, with applications to jets of active galactic nuclei, but also he has a very important job work done on neutron stars. Anyway, today he will talk about AGNs, and I'm very eager to listen to what he's going to tell us. So, Kostas, welcome to Athens, at least even virtually, and you can start. Thank you.
Jay, thank you very much. Thank you very much for your kind introduction. It's a pleasure to be here with you, even virtually, but I'm sure that we will meet very soon again in person, at least this summer for the COSPAR conference, but also I hope that we will have the chance to exchange visits in Athens and Patras. And indeed, I'm interested in problems that involve magnetic fields and excellent sites where we have magnetohydrodynamics problems are neutron stars, but I'm not going to discuss today anything about neutron stars. On the other hand, I would rather discuss things about relativistic AGN jets, and mainly I have preferred to work to present some results on this problem, because I know that there is great expertise at the University of Athens astrophysics group on this kind of problems, and members of the group have made very important contributions. So I'm going to present some work we have done over the last few years in collaboration with Sergei Komisarov and Jean Matsumoto. At some point, all three of us, we were in Leeds. Then I moved to Durham, and Jean was also in Leeds. Now Sergei has stayed in Leeds, and Jean moved back to Japan, and I moved to Greece. So what we are interested in, and the main question that we would like to ask and hopefully provide some answer is what is determining the extraordinary stability of relativistic AGN jets. And what we are trying to do is we want to find states that are stable, states that are unstable, and identify the main qualitative characteristics. And essentially, I would give you the main point of my talk. Essentially, the idea is that jets that start as overpressurized flows since they are expanding within some, and they are confined by some environment, we will go through reconfinement. So essentially, after some point, they will stop their conical expansion, but they will converge. And the thing is that the jet is initially causally disconnected. Essentially, the flow is so fast that if some instability happens, this is not going to affect the entire jet, so we can't have a global disruption. But once we reach this reconfinement point and downstream the reconfinement point, the jet restores causal connection. So this has important consequences. First of all, we expect that the jet will remain stable upstream the reconfinement point. Now, since the jet is following some curved flow, the flow is susceptible to the centrifugal instability, and I will discuss what this instability is doing. And this instability may disrupt the jet, and the way it disrupts it, it has some interesting astrophysical consequences. And we also ask the question, what happens if we have some toroidal magnetic field in the jet? And we found actually that the inclusion of a toroidal magnetic field actually stabilizes this jet. So we have presented this work in a series of 4 papers, initially with Sergei Komisarov and then also with Jin Matsumoto. I will give a very brief background and discussion of astrophysical jets. Essentially, it's a collimated flow of material. We see jets in a variety of environments. We see jets in protostellar objects. Essentially, the combined effect of rotation and accretion, which are related to strong gravity, as well as a magnetic field, lead to some collimated flow, which we see it as a jet. Now, the interesting point is that this collimation initiates in a very narrow region. Probably this is related to the central part of the to an active galactic nuclei, but the length of the jet can be billion times longer compared to the size of the launching region. The main motivation for this problem and the astrophysical motivation is the Fanaroff-Riley dichotomy. In a seminal work, which is almost 45 years old now, well, more than that, Fanaroff and Rayleigh classified radio sources in 2 classes. Class 1 is, or type 1 sources are the ones that are brighter in the inner half of the source. So you see here the origin. This is a radio galaxy 3C31, and you see that it is brighter here. And then the jet expands by flaring, as you see it over there, and it creates plumes. These jets have lower power, typically in the order of 10 to the 44 ergs per second. And there is another class, class 2, which are radio sources that are brighter in the outer half of the source. So actually you see that the brighter points are over here and down there. They have about 2 orders of magnitude higher power, and they are surrounded by bubbles, and they end on hotspots. Now, regarding FR1 jets, they expand well inside the galactic core. They have sizes of a few, up to a few kiloparsecs. The jet flares, so by flaring we mean this behavior where the flow expands and becomes somewhat turbulent, and they are slowed down. So if you see the speed scale to the speed of light, after some distance the Lorentz factor drops. FR2 jets, they are more powerful. They are about 2 orders of magnitude more energetic. They inflate bubbles. These bubbles contain hot but low density gas, which is what is confining actually the jet. And they end on hotspots which are well outside the galactic core. So to keep this in mind, if we want to model some these two different types of jets, we will need to have, in one case, a jet that is confined by some heavy but cold gas. This is the case of the FR1 jets. And for the FR2 jets, we would need to study them by confining the jet with a hot but light material, so high pressure, low density. Now, let's go to the point of jet reconfinement, which is not necessarily applicable only to astrophysical jets. It's a general property of jets, as we are going to see in a little bit. Now, if the external pressure outside the jet drops faster than the pressure inside, the jet becomes essentially ballistic, and it expands in a conical shape. So typically the jet just flows the shape of the nozzle, and it expands as inside the cone. Now, if the external medium, if you think it over here, so the jet starts from this point and then moves to positive Z, as I'm plotting it, as I have in the plot here. Now, if the jet at the exterior drops slower than the pressure inside the jet, what is going to happen at some point? The external pressure is going to overtake the internal pressure, and the jet will start to get reconfined. So essentially, this will lead to some region where the jet reconfines, and formally, this will lead also to some convergence, to a point of convergence down there. So Komisarov and Prof were studying this problem. They were modeling the propagation of a jet in an atmosphere where the pressure drops as k to the minus 0.5, and then in the other case, the external pressure drops as k to the minus 1, the distance from the origin. And you actually see that the jet here undergoes this expansion and reconfinement phases. Obviously, here you see that the z-axis goes up to 4,000, whereas the horizontal axis, the cylindrical R, if you want, goes up to 6. So this is highly exaggerated. But actually what you see is that if the external pressure doesn't drop very fast, you're going to have a shorter wavelength. If K is 1, so the external pressure drops as Z to the minus 1, the wavelength becomes longer. Now, if one makes this K equals to 2, essentially we're going to have a conical flow. We see this reconfinement in non-astrophysical jets. This was actually discussed more than 100 years ago by Mach. We have the so-called Mach diamonds that we see here. You see that there are multiple points of reconfinement, or even here, the jet that goes through this nozzle from the rocket essentially gets reconfined here, and it makes probably 3 or 4 recollimation shocks, and this oscillation of jet boundary has been discussed by Prandtl. So one point that we need to keep in mind is that if we have the expansion of a jet within some environment where the pressure doesn't drop faster than R to the minus, than the distance from the origin to the minus 2, we expect to have these reconfinement shocks. Now here, what happens is that what I'm showing in this case is a jet solution, where actually in red I'm showing the streamlines, and in black in the left-hand side we have pressure and temperature. I would like to focus on the streamlines, and what you see here is that these streamlines converge back to the axis, and then they expand again. So if, let's say, for instance, some instability happens in this region, let's say at this point over there, for this instability to affect the flow, especially close to the axis of the jet, it will need some time. Now, if the jet is moving relativistically, one can do the calculation. So here I have the calculation for some fluid elements A and B that move at 0.9 of the speed of light. And what we get here is that if some signal leaves from this point at T0, it will take quite some time to get to point B. So if some instability happens in this region, it will take, if we have, in this case, I'm having just parallel motion, the difference in time. So what this actually means is that for the parts where the flow is before reconfinement, so upstream the reconfinement point, most of the jet is causally disconnected. So even if some instability happens, fresh material will come from the origin, which is not, that doesn't know anything about this instability that has happened down there, and it will continue the flow. Things will change though once the flow lines converge near the axis. Once the flow lines converge near the axis, it's likely to have some instability. So what we want to do, and what is our hypothesis, is that the relativistic jets are causally disconnected upstream the reconfinement point. If some instability happens, it will not globally disrupt the jet upstream the reconfinement point, but it can disrupt the jet downstream the reconfinement point. So how we are going to treat this problem? We are going to construct some equilibrium solution. We will start from a hydrodynamical equilibrium solution, and then we will use it as an initial condition for simulations. First, we're going to do axisymmetric simulations, and then we are going to do full three-dimensional simulations. The other option would have been to use some jet injection simulation, so to inject some material from the energy and see if this is stabilized or not. The thing is that while this approach is manageable in axisymmetric, in an axisymmetric problem, it becomes exceptionally expensive in 3D simulations because we have to deal with the penetration of the jet into the external medium. So we assume that we have some equilibrium, and then we check if this equilibrium is a stable equilibrium or not. The setup we are using is that initially of special relativistic hydrodynamics, the equations are described here, and what we have been using is the AMR-VAC code that has been developed by Ronnie Keppens and a big team around this group. And for the equilibrium state, what we are using is the approach that has been proposed by Komisarov in his 2015 work. So the idea there is to use essentially this code to construct an equilibrium model. So we are not starting our solution from some analytical equilibrium because it's not guaranteed that we can find a hydrodynamical equilibrium for a jet with all these reconfinements analytically. Essentially, there are no such analytical solutions. What we actually do is that we use we use this code solving essentially a one-dimensional problem. Essentially, we have a jet that propagates in the z direction, where actually the z direction plays the role of time, and then we have expansion on the side, which is the radial expansion, and then we rotate the solution to create the axisymmetric initial equilibrium. We have studied 7 such models, where actually we have essentially 2 families of models. One where the jet is expanding within a uniform medium, and 2 models where the jets expand within a uniform medium, and then some jets where the jet expands within a stratified pressure. So we use a simple King profile for the external density and pressure. Now, what we have in mind is that the uniform external medium, where the pressure, where the density is not as high as is in the jet, but the pressure is high enough. So essentially, we have confinement by a hot but light gas. Is related to the FR2 jets. and the other case is related to the FR1 jets. So we start with this initial condition, and first we perform some two-dimensional simulations, axisymmetric simulations. The reason we are doing that is, first of all, to see how accurate our solution is. So we hope that if we start with this type of equilibrium, the jet will remain in place if we have an equilibrium, and obviously to see if it's stable in axial symmetry. So what I'm showing here is the jet. I have expanded the horizontal axis by a factor of 10 just to see any effects. And the jet is moving here along the z-axis, and you see actually this reconfinement shock. Keep in mind that this is exaggerated by a factor of 10 because of the expansion that of the magnifications that I have used on the horizontal axis. So by running the simulation, you actually see that there are some initial effects here, probably some perturbations because of the interaction between the jet and the external medium. You see here there is some hot gas that creates a wave that moves vertically to the axis. But the jet, the final state of the jet, is very similar to the initial state of the jet, meaning that the jet is not stable. So we started from something like that here, and we ended up with a jet that is somewhat inflated with what we had before. But we don't see any sign of some highly disruptive instability. Then what we did, obviously we did this for all our jet simulations, and we didn't see any signs of critical disruption. Then what we did is that we simulated the same problem using now the MRVAC code, but in a three-dimensional setup. So here you see actually the jet. This is a section of the jet at the edge. So you can imagine that this is essentially propagating from the bottom left to the top right, and over here is the reconfinement point. And as you actually see here is that what we notice is that there is some initial perturbation, but also this thing expands and it starts, the flow starts becoming very turbulent. So what you actually see here is that after some time, the flow has lost its coherence in this region. Now, this is a section of the jet. This is again the density of the three-dimensional simulation. And what you actually see here as I'm running this simulation is that beyond the first, so downstream the reconfinement point, the jet has lost its coherence and it has become a turbulent flow as you see it over there. So there is no second reconfinement point. And obviously the final state, which still expands, has no relation to the initial state beyond this point. Now, if we look at the density, what we had initially and what we had at the end, you see that the flow has changed significantly. The jet doesn't have these clear edges as we had before. And also the Lorentz factor up to this point was about 5. And you see that it has decelerated significantly. Also here beyond the reconfinement point, the Lorentz factor was increasing again. But you see that beyond this point, the Lorentz factor is dropping. It started initially as 5, and then it's somewhere between 2 and 3 in this region. Then what we did, because we wanted to understand the nature of this instability, is that we made a cut at this point, RC. This is the radius of the galactic core to have a feeling of the distance. And what you actually notice here is that near the axis of the jet, so this is what we see if we cut the jet in this region, near the axis of the jet, at the very center, the material doesn't seem to be very significantly affected. So essentially, this is the part the central part of the jet that has maintained is it doesn't have causal, there is no causal connection, so there is no instability. But around this region, we actually see that this instability initially develops by creating these fingers. So you notice here that it's not just a turbulent flow, it's a clear formation of some fingers that can tell us something about this instability. So a similar behavior is noticed in the jet, where we have confinement by light but hot gas, as we have over here. But there are some clear differences. For instance, what you notice in this region is that, unlike the other case where the Lorentz factor was dropping significantly beyond the reconfinement point after the onset of the instability, here the Lorentz factor remains much higher. This is probably related to the fact that the material around the jet has low density, so it's not entraining the jet over here, and it doesn't decelerate it. Again, here we see the temperature of the jet, and this is a similar shape of the edge of the jet. You see actually that this is morphologically different. Essentially, this is creating something that looks more like a bubble around the jet rather than this turbulent disruption. We have also experimented with different opening angles and the different Lorentz factors. So for instance, this is a jet with a Lorentz factor equal to 30, and this is put inside a cold but heavy gas, and you see that the jet is decelerated immediately downstream the reconfinement point. Similarly, we have studied a jet that has a more narrow angle, theta equals to 6 degrees, and the other had 12 degrees. And you actually see that the behavior qualitatively is quite similar to what we had before. And the main difference comes depending on the nature of the surrounding medium. Now, this jet is essentially a jet, is a narrow jet with gamma equals 5. So if I am to summarize the results of these 3D simulations, the first point is that the jets become unstable, it gets disrupted downstream the reconfinement point. Upstream the reconfinement point, they remain unchanged. Now the reconfinement point moves closer to the jet source, and energy is converted from kinetic to thermal. Now we've noticed two clear different behaviors. Essentially, jets where the external medium is heavy, but the jet has lower density, flare and slow down, whereas jets where the external medium is light, but the jet is heavier, may maintain this fast spine and do not expand as fast. Now, what we want to answer is what is the nature of the instability, because obviously we see something that disrupts the jet. This doesn't disrupt the jet when we are in axis symmetry. So in axis symmetry, we see this reconfinement going beyond the first point without the jet being disrupted. But in 3D, this thing seems to work. Now, what are the usual suspects actually for these instabilities? One is the so-called Kelvin-Helmholtz instability, where actually what one would expect is that we would have some fast-moving jet. The external medium is at rest, so this difference in velocities between the jet and the external medium would lead to vortices on the interface. This is the standard picture of Kelvin-Helmholtz clouds. Now, this is not what we see. We never see, at least at the onset of this instability, these types of vortices. Another point that has been proposed, another type of instability that has been proposed in this context is the Rayleigh-Taylor instability. So this kind of instability occurs when we have high density material to lie on top of low density material, and by on top meaning there is some gravity acceleration going from top to bottom. And this leads actually to the formation of the fingers and mushrooms, which are similar to what we have seen at the interface between the jet and the external medium, where we had the onset of the instability. The problem, though, is that this instability in our problem does not only appear when the jet is, let's say, heavier than the external medium, which would give a hint, okay, we have some type of acceleration going from the interior to the exterior, probably because of circular motion, and this will lead to Rayleigh-Taylor instability. But this also appears when the jet is lighter than the external medium, and always points from the jet to the external medium. So it can't be based on this argument, Rayleigh-Taylor instability, which is actually an idea that has been proposed by Jin Matsumoto and Kenji Toma in some papers that they had published earlier. And this is also a characteristic picture of Rayleigh-Taylor instability. You see the fingers and the mushrooms. Now, what we were actually exploring when we were exploring these types of instabilities, we started discussing whether this could be related to the so-called centrifugal instability. So there is a standard textbook criterion about the Rayleigh criterion, where actually if we have some uniform density, axisymmetric and incompressible flow with angular velocity omega being a function of radius, this becomes unstable if the derivative of this quantity omega square r to the fourth is smaller than 0. So for instance, this is something that one can see in concentric cylinders or on a curved channel, or is in a boundary layer of a curved surface. So for instance, if this omega here is higher than that omega over there, and this quantity is has a negative derivative, then we started seeing this instability. There have been actually some flow experiments about this problem. So you see the central cylinder over here is rotating faster than the external cylinder. Probably they are separated initially by some membrane, I suppose, and then once the surface becomes free, you see the development of these vortices that we see over here. And now if you see them from an angle, you notice that they are making these characteristic shapes. If you see them from the side, they look like more like the finger mushroom picture. So we asked the question, how this instability can operate if we have a relativistic and compressible system. So essentially we have a cylinder that is rotating by some omega of r. It can rotate relativistically, and it can be compressible, as is the case of the jet. So W, I remind you, that is rho plus gamma over gamma minus 1, gamma being 4/3 times the pressure. And we have simulated a cylinder where actually the density is the same at the interior, at the exterior, but omega to the left is 0.9. So over here we have 0.9 to the speed of light, and the external part of the flow is not rotating. So if we have the relativistic centrifugal instability, we expect to see something like the vortices that we had in this experiment. And actually, by doing this simulation, you see actually that the interior gets mixed with the exterior, and we have this onset of this instability. We have actually developed with Komisarov an analytical criterion for this case. And this psi quantity that has this omega r square all square that is exactly what we had in the non-relativistic case, but now it's multiplied with W gamma squared. We need the logarithmic derivative of this with respect to R to be smaller than M squared being the relativistic Mach number. So essentially, the Rayleigh criterion for the relativistic compressible case is somewhat different. We have studied this problem in detail. We have explored some different profiles for the flow at the interior and at the exterior, and we have actually confirmed also numerically our analytical criterion. So the main point here is essentially that if we have some curved flow that is confined by a stationary fluid, this will trivially satisfy the instability criterion. This psi will be non-zero at the part where we have the curved flow and zero at the exterior. Now, flows with larger curvature radius will have lower growth rates. And essentially, the instability will saturate once this psi quantity will have on average a non-negative derivative, and the qualitative behavior of this instability will lead to the formation of fingers and these mushrooms. These are oriented parallel to the flow. And also we have found that the axisymmetric modes are the fastest ones growing. So how can this be related essentially to a jet? And what we have here is that this part of the material is stationary. So because it's stationary, this psi quantity is equal to zero. But the part that is inside the jet has a psi that is positive. So what this means is that the Rayleigh criterion for this flow is trivially satisfied, no matter how you take the relativistic or the non-relativistic one. And the jet will become unstable at this transition layer. So actually what you see is that this is the initial picture, and now this part of the jet becomes unstable. Now, higher pressure will develop due to heat, so essentially we will have a higher pressure. So another point that comes here is the fact that initially we had the reconfinement point up to this region. You see here it has recessed closer to the origin. And also you notice here that we have an explanation for the origin of these fingers. Now, the thing that we also want to keep in mind is what is going to happen if we add a magnetic field. So because clearly we know that a magnetic field should appear in a jet. We have discussed that a jet essentially has some, the launching of the jet requires a magnetic field. And what we want to discuss now is what happens if we have a jet, if we have a magnetic field, which is perpendicular to the rotation, is parallel to the rotational axis. So again, here we have the picture of the two concentric cylinders over here. This part is rotating, this part is non-rotating, but we have also added a magnetic field parallel to the flow. It's not surprising that because the instability needs to do some, to preserve the flow perpendicular to the magnetic field, it will need to do some work. And because of that, the instability is suppressed. So for instance, in the previous case, when we had the material rotating in this region and in that region being at rest, when we had full mixture here, by the inclusion of a magnetic field whose dynamical effect, effect in terms is not comparable to the kinetic energy, can suppress the flow. Now, what with the picture that we can have in a jet essentially is that if the velocity is in this direction, right? So this is the curved flow. The magnetic field, a toroidal magnetic field, will be in that direction over here, and because of that, the flow, the instability, we expect it to be suppressed. And we have found also criterion again with the relativistic enthalpy, the velocity, and the magnetic field about the wavelength that cuts off the instability. So here we have again this criterion with some magnetic field, and from left to right we increase the intensity of the magnetic field. And while you see that initially the flow becomes immediately unstable, here with a somewhat stronger magnetic field, part of the internal flow is protected, and then if we make the magnetic field the strongest, you see actually that the instability grows much slower. So what we did for this part of the problem is that we started performing simulations using three models, apart from the hydrodynamical model. We used three models where we included a toroidal magnetic field, as we had in the picture before, where sigma ranged from the maximum value of sigma, the magnetization, ranged from 10 to the -4, 10 to the -3, and 10 to the -2. Here is B phi, and the pressure and the magnetization. So essentially, this is the initial state, but now we have also a magnetic field that you actually see here. So the magnetic field is strongest at the boundary of the jet. Again, we use the same technique to construct the initial condition. So here the toroidal field is positive, here it is negative, and it's kind of forming some rings. The Lorentz factor here has a maximum value of 5, and over here we have the tracer, which is 1 if we are within the jet and 0 otherwise. Now, once we started including this toroidal field, we actually noticed that for the hydrodynamical model, obviously, we have the results that we had before, but for the model where the toroidal field had a magnetization of 10 to the -4, even in that case, you actually see that the reconfinement point is not pushed so low as it is here, and the flow appears less turbulent. Now, if we have the model where the value of sigma goes up to 10 to the -3, you actually see that the flow is not disrupted significantly. Essentially, we have an M equals 4 mode, and then if we have the strongly magnetized case, and by strongly magnetized case, I mean a sigma of 10 to the -2, you actually see that the jet is not disrupted at all. So just to have, again, a picture of the jet shape, over here you see the hydro model, you see the flow is disrupted as we had before. When we have a sigma of 10 to the -4, you see that the flow is disrupted, but it's not becoming as wide as it has been before. A sigma of 10 to the -3, you actually see that it makes essentially this cross. This is essentially the maximum wavelength that we can have. So this puts an M equals 4 mode. And then for sigma of 10 to the -2, you almost see that nothing is really happening. And this is more or less true because the jet flow, remains almost stable. So we have performed calculations with different gammas and different sigmas, and we actually have found that the critical state that goes between unstable and stable behavior, that's for the cylindrical simulations, is between a sigma of 10 to the -2 and a 10 to the -1. So the main point then is essentially that we have a model that can provide an explanation for the stability of jets. So again, as we said before, the jets expand and get reconfined as they propagate. We have the initial state where the flow is causally disconnected. So no matter what is going to happen at the boundaries of the jet is going to be stable, at least globally. And if some local instability happens, it's not going to affect the global flow. Now, once the jet gets reconfined, the flow will become curved, and streamlines will converge to a narrow region. Now, what we see then is that the jet is unstable upstream the reconfinement point, so that's between the origin and up to the reconfinement point. Now, because we have curvature, the jets will be susceptible to centrifugal instability, and this will disrupt the flow downstream the reconfinement point. The way the flow is disrupted depends on the external medium, so it can be either flaring or either with the development of a long spine and a hotspot. And once we start including a toroidal field, even if toroidal field is dynamic and subdominant, it will stabilize the flow. This is an interesting point, and I think it's worth keeping this result in mind, because there is a lot of literature recently about jets that are disrupted because of current-driven instabilities. And I have no objection to that, but what we find here is that there is a wide region where we can have a jet that is stabilized because of a toroidal magnetic field, and there is a broad region, let's say, in the parameter space where the flow is magnetized, but then it's not going to be destabilized by some current-driven instabilities. So I would like to stop here, and I'm happy to take questions, and thank you very much for your attention. Thanks.
Thank you, Costa. Very interesting talk. And now let's open the discussion. So please either raise a hand or take the microphone. Unmute yourself. Oh, okay, Nectarius, I see.
Yeah. Hi, Costa. Thank you for the nice talk. Very nice talk. Yes, so let me ask you first, how you define the sigma, the magnetization?
Okay, so we use the standard definition for the value of sigma. Let me check if I have it in some backup slide. I think I have it here, but it's defined using the magnetic field at the jet frame, and then I divide it by the relativistic enthalpy.
Ah, okay. You take into account the enthalpy as well.
Yes.
Which is, remind me, the values of enthalpy is 100. You showed in some cases.
Yes. It's something like that. Yes.
If you do the same with colder jet, let's say enthalpy of the order of 1, do you have a feeling what will be different?
Right. So if the jet is colder, I'm expecting probably to have to be stable in a longer wavelength. So I think let me check this criterion that we have over here. So essentially, by changing W, so we compare W at the, you can see my screen, right?
Yeah.
Yes. So by changing W at the interior and W at the exterior, if this W becomes smaller, this lambda will become longer.
That would be the only difference.
That's the analytical heuristic criterion we have got about this problem. I mean, it's essentially that we obtain this criterion not by doing an eigenmode analysis, but we used again the derivation of the Rayleigh criterion with this psi essentially.
Yeah, yeah. Mm-hmm.
Yeah.
At some point you mentioned that Taylor instability is not the case here because you see the same behavior when you have lighter or heavier jet compared to the environment.
That's true, yes.
In this comparison, you take into account only the density or the product density times the enthalpy?
I take into account the product density times the enthalpy. So we were actually thinking of that initially because we were thinking, okay, this is going to become heavier because of the relativistic term compared to the external material that is at rest. But we checked that, and this was not actually the case.
Okay.
Yeah.
Nice work. At least we have one example where the magnetic field, the toroidal magnetic field, stabilizes the jet, because usually it destroys everything. So it's good to have actually, at least one case.
That's what I mean. We have well, I didn't want to go because this goes more into a fluids dynamics seminar rather than an astrophysics seminar. But we have gone through the MRI instability and the current-driven instabilities. We have an entire section where actually we compare the wavelengths of the MRI and the current-driven instabilities. And for the MRI, we expect that the wavelength will be longer. So the wavelength, you can imagine that if you had an infinite cylinder, you don't care how long the wavelength is. But here, because you have curvature in one direction, but also your jet has a circular cross-section, the wavelength cannot be longer than the circumference of the jet. So what I'm trying to say here is that if you think that this is the circumference of the jet, if you cut off the modes that have wavelength up to the circumference of the jet, then you are safe. Whereas in a cylinder, you can make it as long as you want.
Yeah. A last question.
Sure.
You start with this analytical solutions, or not analytical, numerical solutions by using this trick, replacing T with Z.
That's true, yes.
You think that this is not critical for the result?
Right. So,
but you don't have another example, I mean, to start with something different. Did you try to start with something different?
Yes, we have failed attempts. No, what I'm saying is that yes, we have started with this family of equilibria, and we have used it as an initial condition in 2D simulations, and we have seen that there is some disruption here, but the jet goes back into this equilibrium. So well, probably not identically, but very close. So actually, we think that this is a good representation of the equilibrium that corresponds to the boundary conditions of an outflow at this nozzle and axis symmetry. We haven't tried some other equilibrium, so we have used this technique to develop our initial condition. I'm trying to think what other equilibrium one could find. So
it's not trivial, but I just asked the
I'm just thinking. Yes, I'm thinking loudly. Yes, I think that probably yes, this equilibrium is a good representation of what we would get from an axisymmetric jet.
Okay, I will think about it, and if I found something, I will tell you. I mean, just
Actually,
to have another case, to start with something different, to see.
Yes, actually, what we have been thinking, and I have been thinking, is that obviously one should, what we want to do is to push into some higher magnetization, so to see if we start, if we will be able to start triggering the current-driven instability.
Other kind.
Yes, exactly. So once the magnetic field is not subdominant, and the other problem, but this is not, this requires higher computing resources, is to start working with an injection simulation. So we have worked on injection simulations in axisymmetric, and we have seen qualitative differences between the unmagnetized and the magnetized cases. We have done actually a study of the parameter space with a student in Patras, though we are still working on that. But we haven't done this yet in 3D because it's computationally very demanding.
Okay, thank you.
Yeah, thank you very much.
Okay, Maria, I see that has a question.
Yes, so it's, I think, very related to the last point that you were trying to make, and maybe it's a naive question, but let me ask. So I didn't quite understand, or maybe I missed it, if this, how you start the simulations in 3D. So you mentioned that you had this solution, the equilibrium solution for the 2D, and how do you start your 3D simulations? This is the first one.
Okay.
And the second one is that if you don't actually start you don't simulate the jet from the very beginning using these injection simulations that you mentioned in 3D, how are we sure that the jet will get to this equilibrium that you then study, and you add the toroidal magnetic field, and you say that the toroidal magnetic field stabilizes the jet? So is it possible that the jet will be disrupted even before reaching this state?
Okay, yes. So let me come first to your to the first question. So for in order to construct the initial state, what I'm doing is that I'm essentially integrating in time a one-dimensional flow. So my time evolution is then replaced by the z-axis, and then I see how the jet, this line expands or contracts, and then I stack these lines one on top of the other, and I construct the axisymmetric solution. Then what we do next is that we rotate this configuration, and we initiate the three-dimensional simulation. Now, we do this initially without any magnetic field, and then for the magnetic field, for the MHD simulations, we include the magnetic terms in the 1D solution. So essentially, we start with something that is an equilibrium, and we test it in axisymmetric simulations just to be sure that we are not missing something. That's the first question. Now, remind me.
The second one was, yes, the second one was the following. So I was wondering if it is possible, when you simulate the jet from its very beginning and it is magnetized, and you follow the evolution of the magnetic fields along the jet, if it is possible disrupt the jet before you reach the equilibrium that you use in order to study the stability afterwards.
Okay, yes. So this, yes, I understand now, yes. So this kind of, this study will require an injection simulation. So essentially to start from an empty, let's say, domain and start injecting the jet from the base. Unfortunately, we haven't, we prefer to start from an initial equilibrium because the latter would have been very demanding computationally. And because of that, we prefer to check if these solutions are stable. Now, I think that physically is relevant to do the injection simulations. We are actually, this is among our plans, but we are trying to find a way to do this without with using the optimal computational resources.
So maybe it's not resolved, like that the toroidal magnetic field might not necessarily stabilize if we don't have this situation happen.
Yes, actually, we have been thinking of that, and the main point is if the magnetic field maintains its toroidal structure for so long. So possibly, if we start with a 3D simulation, we inject it with some toroidal field, maybe it will not survive too long. So this is a possibility. Yes.
Okay. Thank you.
Thanks.
Okay. Harris, I see, has a question.
Yeah. Thank you for the really nice talk. I would like to ask a few things on a couple of points. The final simulations that you showed us, they were only toroidal component of the magnetic field, or you had also included the Z component, BZ?
No, in these simulations, in the initial conditions, we only had a toroidal magnetic field. We didn't have any poloidal component for the magnetic field.
Oh yeah, I see. Have you tried, or are you thinking to try in the future including both components? Do you think that the evolution of the jet will change if we have both components present?
I mean, I expect to have some changes. Though what we are finding so far is that the toroidal field is sufficient for the stabilization, and maybe because actually the way the modes of this instability work, they are perpendicular to the toroidal field. So if you draw the let's say the wave vector of this instability, it will be normal. It will be, if you want, actually parallel to the toroidal field. Now, if we had a poloidal field, my first reaction is that this will not affect so drastically this particular instability. But it's certainly a problem worth studying, actually.
Yeah, I see. So the toroidal component gets to stabilize from a magnetization from a specific value from magnetization upwards, stabilizes the instability. Is this due to the tension that the BFE introduces, or is it something else that the field gets to suppress the instability?
Yeah, no, it's essentially this tension. So if you, I don't know if you can see my screen. Essentially, what is trying to do here? That's the case of the inner. This is a setup where the inner cylinder has a fluid that is rotating, and the outer cylinder is at rest. Over here we have some magnetic field in the Z direction. But remember that in the cylinder, if the field is in the Z direction, in the Z should be in the phi direction, just to keep this analogy that we have over here. So then what is actually happening is fairly straightforward. It's trying to maintain its shape. So we have the tension, and the tension opposes stability. Yes.
Another point, if for the magnetization, up which value did you try to see? I mean, what was the highest magnetization value that you tried?
For the jet, the highest magnetization that we had was 10 to the minus 2, because we stopped there since the jet got stabilized.
I see, I see.
In the other family of simulations, we went up to the 10 to the minus 1. Because these are the co-rotating, the concentric cylinders. The reason we did that is because we started cutting off longer wavelengths. So we wanted to go to a longer wavelength, whereas in the jet, the maximum wavelength that we cared about was the circumference of the jets, of a jet section.
Okay, I see.
So actually, in this plot, I think we are. These are the concentric cylinder simulations. The horizontal axis is gamma. The vertical axis is sigma. And we notice that between 10 to the minus 2 and 10 to the minus 1, the flow is stable. And the maximum sigma that we got here is probably 4 times 10 to the minus 1. Which is stable, and we don't see the onset of magnetic type of instabilities.
Yeah, that's my thought. And one last question: after you stabilize the centrifugal instability with the adding of the toroidal component, you didn't notice any other type of instability arising at any point in your simulations?
Yes, so if this is essentially the case where we have sigma 10 to the minus 2, and essentially what you actually see here is that the jet remains more or less unchanged. So here actually the time is running, but you actually see that the jet is not changing drastically. So this essentially stabilizes the jet, and it stays as it was.
So I mean, I would expect some point, some kind of Kelvin-Helmholtz stability to arise, but it is stabilized due to the curvature of the jet, the causality process.
Okay, so the Kelvin-Helmholtz instability is probably stabilized because of the causality process. Even if we go over here in the axisymmetric simulation, this is without any magnetic field, you will actually notice that there are some small features at the interface. Probably you can see them. You can see them over here, which are essentially related to the vortices of the Kelvin-Helmholtz instability. If I had this in higher resolution, you would see that you have these features over here that are the Kelvin-Helmholtz features, but they never managed to make into the jet and disrupt it.
I see. Okay, thank you very much.
Okay, thank you. Thank you very much for the questions.
Okay, long discussions, I see. Is there any other question from the audience? Okay, we went quite along. I have a very short one. I have asked also Nectarius, but I can't remember the answer. Are we sure that we know all these types of instabilities that occur in these jets? I mean, is it possible that something has escaped?
Well, I mean,
because you said.
Well, I mean, let's say the centrifugal instability, the relativistic version of the centrifugal instability, we have searched quite a lot with Komisarov, and we haven't found anyone suggesting before that this instability may operate in jets. So at least this was a new addition at some point. Okay.
Maybe there are more.
Pardon?
Maybe there are more.
Yes, I hope so. Yes, this will be good for us.
Okay. So, Costa, thank you very much for again for your very interesting talk. And I think we will stop for